So I've copied the equation from before, so we'll need that again later. What I want to do is let's take the energy equation for each of the fluid streams that we have up here on the left. This is just saying like the heat transfer is related to C dot delta T for the hot and the cold streams. And then let's sub in our definition now of Q dot. All right, so we can rewrite these basically as follows. All right, so we're subbing in, definition of effectiveness. So this would be TC out equals TC in plus, let's see, effectiveness. So effectiveness times C dot min times THN minus TC in divided by C dot C. C dot C. And then the second one is TH out equals TH in plus, again, effectiveness, C dot min, TH in minus TC in over C dot H. Okay. So I have, using the definition of effectiveness and the energy balance on each of the flow streams, converted that into this equation, these equations here. That's fine. So now let's take that and plug that into the equation right above it. And then we're going to kind of get closer to the end result here. So I'm going to take these, and where I see, let's see, TC out here, TC out here. I have TH out here, TH out here. I'm just going to sub those in and collect the terms together. So that looks like this. Ln, again, big bracket. So we have TH in minus TC in. This factors out to 1 minus epsilon C dot min over C dot H divided by THN minus TCN times 1 minus effectiveness C dot min over C dot C. Okay, that's equal to minus UA, 1 over C dot H minus 1 over C dot C. Okay. Where can we go with this? So we say, if we look at the left hand, we can say that the temperatures cancel out, which is nice. So that goes away. And we're left with actually an expression. So we could further simplify the left a little bit. We will subsequently. But first, before we do that, we're left with this expression that's saying the performance of my heat exchanger, doesn't it actually involve the temperatures? Right? So we've gone through the trouble to use energy balance and effectiveness. We have this definition of effectiveness in here, but the temperatures no longer appear. So if the temperatures happen to be exactly balanced like they were in the LMTD case, you don't have a problem, right? It doesn't blow up to infinity or something like that. You are able to represent this without even relying on the temperatures. This also means that this is generalizable, right? Just like the convection correlations where you're doing things in terms of non-dimensional numbers and Nusselt numbers and things. This is generalizable to like any set of heat exchangers that you want as long as it's counterflow, right? So this is for counterflow. Okay, so where to go with this? Now let's simplify this down further. So I've got that here. Okay, what we need to do to further simplify. So you see in the upper left, we have C dot min, we have C dot H, and we have C dot C. So what we need to do to move any further is to actually decide which of these C dot C and C dot H is going to be the min and which is going to be the max. Functionality here. Don't we have to know something about which is which in reality? No, actually. What you need to know is that you pick one and it ends up canceling out in any case. So we just have to pick one and then we move forward. So let's just say moving forward, C dot C happens to be the minimum one, C dot min, and C dot H happens to be the maximum. You can try it the other way if you're sitting at home and really doubt what I said. I'm sure you want to do that. But let's go ahead and sub those in. So this becomes simplified like this. So ln of 1 minus epsilon c dot min over, okay, so now c dot h was c dot max, so this will be c dot max. Then divide by 1 minus epsilon c dot min over c dot c was c dot min. Okay, and then the right-hand side becomes minus ua, 1 over, let's say, c dot h, so that's c dot max, minus 1 over c dot c, which is c dot min. All right, so what can I do with this now? Well, c dot min over c dot max on the left side, that's capacitance ratio. Right? This is CR. So we can sub that. C dot min over C dot min, this is 1. So that helps. On the right-hand side, we're still left with this C dot max, C dot min thing. It would be nice if we could just express this in terms of CR as opposed to these C dot min, C dot max. So let's do this. Let's take the right-hand side and let's multiply everything by C dot min divided by C dot min. Okay, so UA becomes UA, here, let's move this over here like this. UA over C dot min. Okay, get rid of this, C dot min. And then let's distribute the C dot min through this part in here. So C dot min, C dot min. Okay, again, how does that help us? So now we have C dot min over C dot max. Right, so this is CR. C dot min over C dot min, this is 1. This here, UA over C dot min, you might recognize, right? If you were paying attention a couple slides ago, this is NTU. So we can go through and rewrite this now with our nice simplified format, which is, do I have room? Yeah, so ln of 1 minus epsilon CR over 1 minus epsilon is equal to minus NTU times CR minus 1. Okay? So all that work, now we have this relationship between effectiveness and NTU. So keep in mind, we can always relate UA to NTU. We can plug that in. We can now compute the effectiveness if we were to want to solve this for effectiveness. So this is a really nice, tidy way of representing the performance of your heat exchanger. And we'll use this as part of a system of equations, right? If we wanted to, which I'm sure we do, we want to solve for effectiveness directly. So if we solve this for effectiveness, we get effectiveness is equal to 1 minus, now exponential of minus NTU times the quantity 1 minus CR divided by something similar, 1 minus now CR exponential minus NTU, 1 minus CR. Okay, so now I could just plug in the NTU, get effectiveness directly. Remember, this is for counterflow, all right? And I'll show you on the next slide what the differences look like. Some other stuff that kind of happens here. So let's imagine there's a situation where capacitance ratio is 1. What happens? So you have 1 minus capacitance ratio of 1 is a balanced heat exchanger. That top term becomes exponential of 0. So you have 1 minus, what is this? Exponential of 0, right? So the top term becomes basically just NTU. Let's see, this is for CR going to 1. So the top term becomes NTU, the bottom term becomes 1 plus NTU. This is sort of how it simplifies out. Right, so this is if CR is equal to 1. If CR is less than 1, then you have the result on the left side there. Okay. I think there were some additional steps in there and how we got to this result, so it's not just like it directly, but if you sort of solve it out, it becomes that. Any questions on this part of it? Okay. You guys are quiet today. All right, so let's look at some other examples here. If you go to the textbook, you can find other examples of like this relationship, the effectiveness NT relationship for different situations. So this is from table 12.2 in the textbook. I'll just zoom in a little. So you look at like the flow arrangement on the left-hand side. So if you have a situation where it's counterflow, that's what we just derived. Right? That's the second row there. So that's counterflow, and then there's a capacitance ratio consideration. If you went in parallel flow, it'd be the one below that. Notice it's almost the same, just slightly different. If you have what's called a crossflow heat exchanger, right, so this is now where the heat exchanger is not like, the fluids aren't directly parallel or directly counter, one's crossing the other's path, then it goes as the bottom there, yeah.
Just going back to the previous slide about OCR is equal to 1.
But you can be confident that at least the final result is accurate, right? Because it's been derived, it's sort of here. You can be confident in it, but it'd have to show you how you got from one to the other. Okay, so then we're talking about parallel versus counter. There's these different configurations. So the different fluid types would be shown there. What you can do is you can actually go to ease, and it'll give you like images of what these look like. So it'll have like tubes maybe weaving in and out, or different situations that might apply for what you want to look at.